Hi there, everybody. My name is Amelia Thompson, and I am your host of the Worth Electronic webinars. Now, I am back in the office, and nearby are my handy dandy crutches. And as you might remember, I am a bit of a coffee fanatic. So they do have a cup holder, and it's anything I need to hold my cup of joe. I am really excited to be back with you. It has been a couple weeks. But today's webinar, we are diving into the ins and outs and design and benefits of the coaxial connector. Today's presenter is Thomas Robach. He is the ICANN Technical Academy Principal in Germany. Now, as a reminder, if you have any questions throughout today's presentation, simply ask them in the questions box. I see a few questions coming in. Go ahead. Wish me a good morning, good afternoon, good evening, wherever you're located at in the world. You can make sure that your questions are going to come through to us. Now, if your question doesn't get answered, maybe you think of them a little bit later, or if you want some free samples, if you need a quote, you can always just reply to the follow-up email. It's here for you at we-online.com. And that'll come directly to myself. We can get you those samples, those quotes, answer your technical questions, anything that you might have. As a reminder, because you registered for today's webinar, you will automatically receive the recording, the video on demand, as well as the presentation slides. It's going to come to you within the next 24 to 48 hours when they become available. Don't forget to register for our next webinar. Fabio Costa returns with Jose Guerra. They will be presenting a connectors Q&A in Portuguese and in Spanish next week on August 11th. And then on the 18th, Nick Amy from our sister company, IQD, with our crystals and oscillating products, he will present practice measurement of crystal circuits, how to ensure the system is not vulnerable to process variance in production. Of course, that's on the 18th. Register online at www.we-online.com. Have a few questions coming in. Looks like we have hello from Denmark. Hello, and thank you for joining us today. Have a few hands raised. You might have questions about how you can get your samples. We're just really happy to have you here. Of course, all of our webinars are made possible thank you to our exclusive sponsors right next door in Minnesota, Digi-Key Electronics. I also want to mention that if you can't get enough of my voice, then you can hear it every week with our new podcast. Each week, I'm bringing our application notes, blogs, press releases, and of course, our webinars to a completely audio format. The Worth Electronic What's Up radio podcast available on iTunes, Google Podcasts, Spotify, everywhere where you would hear a podcast. You'll hear me. And now we're going to begin today's Worth Electronic webinar with Thomas Robach, Function and Design of Coaxial Connectors.
Thank you very much for the introduction, Amelia. So, hello everybody, it's my pleasure to tell you something about function and design of coaxial connectors this afternoon, and I will share my screen with you so that you can follow the presentation. And yeah, I think we directly go into the topic as we have just an hour of time or a little bit more. So, today's topic will be as well coaxial systems. So how are they set up? What do we have? How to choose? But we also will go into the basics of RF engineering as it's necessary to understand how to best put or merge the connector with the PCB. And for that reason, we also have an overview over common PCB structures, benefits, things to take care on, some tips and tricks. And in the final chapter, we will combine the connector and the PCB to see what we need to do it in the best way. And we will also see this in some simulations that we made up to visualize the effects that will occur. So let's go for the first chapter, which is types of coaxial systems and mechanics. Well, we have a quite wide spectrum of coaxial connectors meanwhile, which reaches from SMA, reverse polarity SMA, MCX, MMCX connectors if you need something you don't want to screw but you just plug and unplug, as well as the small formats like SMP, SMP, or the very tiny UMRF that you might know from the market as UFL, which is a brand name. So for us, it's UMRF. Well, where to know or how to know what to choose where? We have some tools that I entered into presentation for you to make it easier to select the right connectors in the coaxial spectrum. On the first step, of course, by frequency range that you need. So you see we are going up to 18 gigahertz with our portfolio with the SMA and RP SMA. Then by the size of the connector, so form factor from smallest to biggest. Ease of use, convenience on use means, well, how much do I have to do when I plug it, when I mount it, want to connect it together? Of course, MCX, MMCX with just plug and unplug is much easier than SMA, where I have to screw. I probably need to take care on the tightening torque and so on. And finally, the safety in vibration environment. So how strong, how stable is this connection in use? The same tool for choosing, like for choosing the connectors, we also can offer, of course, for choosing the fitting cables that we also carry in the portfolio. And well, I don't want to go to the single cables, but also here you can choose by frequency, by outer diameter, which is of course important if you want to do the cable connection by yourself. So if you want to merge the cable with the connector by yourself, bending radius might be an issue depending how much space you have, how narrow it is, and of course operating temperature. That's just a small and short overview about the portfolio line. That's all for it. We will take a closer look now on a few things of the SMA connectors, because this is our widest portfolio with the biggest frequency range, and that is the one we also choose for the simulations to see what impacts we have with the different design tools and changes. And so it makes sense to introduce to you a little bit the parts we will use out of that portfolio. So for SMA, of course, we carry the full portfolio from PCB panel connectors as well to different adapters and all the cable style, and of course also the tools to correctly mount them together or fix them together without hurting the thread. What we will use today is some different parts of the SMA connector that we extra choose for certain reasons. The one thing is we will use two different end launch connectors for our simulations because they are very popular. They are available with different pin sizes, which we will see afterwards. And they are quite good from their geometry to transmit higher frequency signals. So this is quite optimum for that kind of signal transmission. We also will show an option for a vertical version and how to adapt your layout to be used with a vertical connector that's not going in line with the PCB track. We also have a full SMT solution, well, because you know the end launch, you have to slip over the rim of the PCB, which is in mass production not always convenient. So with the full SMT part, you have to take care on a few other things in your PCB layout and cutouts. But finally, if you have done this, you can use it for high volume production easily with full automated process. And of course, we also have a fully automatic version for the vertical one. That's the part that we will see later on also in the simulation, and this is the reason why I introduced them at this point. Well, as always, coaxial connectors consist of an interface part that defines the type of the coaxial connector, and of course a body part that defines the mounting style on the PCB. Also, we have a few parts inside, and this is why I'm showing this is, well, it's not so easy. We have to take care, especially if we are talking about angled connectors, on how we set them up inside. And this is also quality criteria, because as you can see here, this is a center contact. This is made of one piece. And this is, of course, the optimum version, to have one piece without any breaking point, whatever, that could disturb my signal. But this is not always the case. So it's really a matter of quality of a high frequency connector, if these angled pins are one piece or if they are soldered in the edge here, which brings additional material, which brings additional influence from the capacitive side and could cause you some issues. On the other side, we have to really take care on the mechanical setup of the connector, which is also a matter of quality for those kind of connectors, because we have to stabilize the distance between the inner center contact and the outer body contact with our insulation material and or the electric material, however, what you prefer to say. And we have to make sure that this distance is completely stable and nothing can move. As well, the insulator should not be able to move forwards, backwards, or turn, but also the contact within the insulator should not be able to move. And this is not always too easy under every circumstance. The reason is, the bigger I make structures to fix the contact in the isolation, the more impact this has on the high frequency, which has a very short wavelength. So the bigger the structure is I use for fixation, the more problems I have with the high frequency. And so you can also recognize on the structures used within a connector, are they more for the lower frequency or higher frequency? The more fine the structures get, the more they're suitable for the high frequencies, but the more complicated is it to fix them in a way that really nothing is able to move. So that's a little bit the balance you have to find when you create this kind of connector, and this is also the quality criteria you can have a look at when you want to see, is this high quality connectors or low quality connectors. And of course, things like plating thickness, used materials for center contacts, are they just stamped or are they made of a flexible material like copper beryllium that allows to use them over a long time and have a stable tension on the contact. We offer our connectors also, like many others, with two different kind of center contacts, and that is what I told you before, where we come back to. We will have a look on our we will have a look on our end launch connector as well, with the big blunt post center contact and the small flat tap center contact, because they have a little bit of a different use, where you should or could use them, or if you use them, let's say, in the wrong way, it's not really wrong, it's possible, but it makes more effort to reach a good result. Due to their appearance, the big blunt post pin typically has a better mechanical contact, of course, to the PCB, but it makes a little bit more effort in the transmission line design, especially if you want to go to high frequency, where you typically have small transmission line width. So it's a little bit more effort to conduct them in a good way to create low losses. With the flat tap, well, the issue is more the mechanical thing. They are very tiny, very small, and if you mount or if you bring them to the PCB, you have to take care not to touch the rim of the PCB to bend them. You have to take care when you solder them not to apply too much solder paste because you get a lot of capacitive parasitics in comparison to the volume of the pin when you add too much solder paste. But therefore they are easier for high frequency design with small transmission line width, as they do not bring a lot of additional volume, and so it's easier to correct the impedance mismatch in your design. What else do we have? Yeah, by the way, as we are talking about end-losh connectors, they are of course limited in their use on PCB thickness. They're typically made for a certain PCB thickness, for example, like we are offering here in the 1.1 millimeter and 1.6 millimeter PCBs for that one. But if you have something different, if you want to go to bigger or thicker PCBs with thicker layer stacks, then you could use as an alternative part this one with the hooks at the end. So the basic geometry on the front side is the same like on an end-losh connector, but it's put from the top side on the PCB, so that this ground hook, I would call it, is going throughout the PCB, and so you can use it to PCB thicknesses up to 2.8 millimeters. But of course, you need to adapt the PCB design in comparison. So the layout needs to be different in the connection area than for an end-losh part. So just to summarize quickly, for the mechanical connector, we are working in areas between -65 to +165 of operating temperature for the SMA spectrum. We have 500 mating cycles, and we are going up to 18 gigahertz with these kind of SMA connectors. And we heard blunt post is more, if you want an easy design, it's more for the lower frequencies, but it has good mechanical contact. The flat tap is easier for high frequency design, but mechanical stability is, let's say, limited. And of course, end-losh is for defined PCB thickness, but there's alternatives where you can raise your PCB thickness. Then let's dive into the basic RF engineering a little bit. We will talk about wave characteristic, about reflection and attenuation, S parameter and VSWR, discontinuities and TDR measurement, to bring some of the basics back to your mind. I'm pretty sure you already have been in touch with it, but it's just to bring us all to the same point, and maybe there's the one or other thing that comes up that has been forgotten over time. So the wave characteristic, of course, we start with the frequency. It's the number of cycles per second. So if you have 10 cycles in 1 second, you have 10 hertz, of course. That's the very easy one. And depending on the frequency, we have a changing wavelengths. So the higher the frequency is, the shorter the wavelength is. And this is shown in the relation lambda is C divided by F. So if you have 1 gigahertz, you have a wavelength of 30 centimeters, 2 gigahertz, it's only 15 centimeters, and 4 gigahertz is 7.5 centimeters. But this is, of course, only if you do not have the influence from the material. If we now add to the whole thing the influence of the material, it looks a little bit different, because if we have our wave traveling through air, then it's correct that we have at 1 gigahertz 30 centimeter of wavelengths, because the epsilon r of air is 1. So the relative permittivity is 1, and that's the material parameter that influences our wavelengths here. And of course, μr, so the permeability for the electromagnetic field, is also a parameter that influences the wavelengths in this case. So if we now send our wave instead of air through a PE material with an epsilon r of 1.5, the wavelength and the same frequency shrinks to 25 centimeters. And for epsilon r of 2 in a PTFE material, so a Teflon material that we typically use as insulator or dielectric material in our RF connectors, the wavelength shrinks down to 21 centimeters. So we do not have, so we have really impact of the material parameters on the traveling wave or on the wavelengths by changing materials. And so you can imagine that we get a lot of issues when we change the materials, but we have to do. We are coming out of a cable with a certain dielectric material inside, going to a connector with probably another dielectric material inside, going down to a PCB with a FR4 material that also has a different dielectric value. And in this case, we even changed the geometry from a circular to a rectangular geometry. So this will cause us a lot of trouble that we have to balance in the design. And we can see also here in the formula of the wave propagation, of course, the factor C divided by square root epsilon r multiplied by μr, so relative permittivity and permeability, that are the material parameters that have influence. The next thing is what we have to take care on is to really differ between wave characteristic, so wave impedance, and the impedance of the transmission line. The wave impedance is really the impedance, the own impedance of the traveling wave, and it's only affected by the environmental parameters μr and epsilon r. That's all. That's the characteristic of the wave itself. Typically, it's 50 ohm. And on the other side, we have the line impedance. And this is now the property of a line to transmit an electromagnetic wave. And this depends on the materials used and on the geometry of the transmission line. And in ideal case, of course, we will match between wave and line impedance to create as low losses as possible, but unfortunately, it's not always optimum in life. Just an example, if you look on the line impedance of a coaxial system, we have also the formula for the characteristic impedance of a coaxial system. And we can also find in this formula on the one side, the characteristic, the material parameter epsilon r, so the relative permittivity of the dielectric material. But we can also find the geometry of the system, because the capital D is the inner diameter of the outside conductor, and the small d is the outer diameter of the inner conductor, so means the range of the dielectric material here. And this is also respected in the formula. So we have material parameter and we have geometry of the system. Good. Next step is reflection and attenuation. In an ideal world, we would say we have the same impedance for the source as for the transmission line and for the load, normally 50 ohm. And if we can arrange this, then we have a perfect match and we have no losses. Unfortunately, that's not working, and typically on the, let's say, interface areas where we come from one point to the other, we create reflections, and reflections for us always means a mismatch in impedance, and this means we are losing energy. And that's what we, of course, want to avoid. What kind of losses can we have over our transmission path? Well, that's on the one side, absorption in the dielectric material. We saw that we have the signal traveling on the signal pin with the electric field pulsing 90 degrees to it throughout the electric material. So you could say the electric material, the epsilon R, is something like, to say it easy, like a resistance to the electrical field, where you lose energy with the field passing in the electric material. Then we have the typical heat loss that we have on every conductor where we put energy or a signal on. So it's the Joule effect that happens in the conductor. We have radiation loss, so means leakage in the environment. So if we have probably not well closed shielding, gaskets, things like that, create radiation loss. If we have, for example, to stay with SMA connectors, if we do not close the locking, so the thread of the SMA connector correctly, we can have leakage, things like that. And of course, we have losses created by reflection. So this means we have variations of the impedance, where we have impedance mismatches, and this also causes loss of energy. How could we now visualize what kind of loss we have, or how much loss do we have, or how well we are matched? This can be visualized either by measurement with S parameter or by VSWR, so voltage standing wave ratio. We can make measurements with S parameter to measure the reflection of or throughput. So if we measure S11, we send in a signal to the measurement device and measure how much reflection we get, or we can measure S21 throughout the whole transmission line to measure how much loss we have throughout the whole transmission line, but this then contains all losses on the line and not only the losses by reflection. So what is important is, if we want to calculate with that kind of measurement, then we are in the power domain, means we have a logarithm on a 10th base. On the other side, we can measure with the relation between forwarded voltage and reflected voltage, and this is what we call the voltage standing wave ratio. And here it's different. We are working on the voltage domain here and not on the power domain. So if we want to calculate it, we have to take care that we are using a logarithm on a 20th base and not on a 10th base. What does this mean in practice? Well, the one is going exactly the other direction than the other. It's exactly opposite to each other. If I have if I'm measuring my return losses as parameter, if it's infinite, I'm very well matched, the best I can have. And up to an area of around 15 dB, I'm still in the matched area, so everything is fine. If I go below that, I'm getting to areas where I'm not that well matched. Typically, of course, this is not a 100% rule. It depends, of course, what I'm doing. Sometimes if people are working on measurement equipment and developing measurement equipment, they might probably allow less tolerance here. Yeah. So if it has just to work, then it's fine. The VSWR is exactly the other way around. So the perfect VSWR, the perfect ratio, if I have no loss between forwarded and return voltage, is 1, of course. And up to a value of 1.4, we can say we're in the matched area. Up, and if it's getting higher than 1.4, then we are getting to the areas where we are have poor matching, or where we are not matched at all anymore. To have a little bit of idea, so if we talk about a return loss of 15 dB, we have 97% of insertion and 3% of reflection. If we go down to 6 dB, we have already 25% of reflection, so quarter lost. That's already a lot. So with our border here from around 14 to 15 dB, we are talking about 3.5% of reflection, not more. Out of that, we are not in the matched area anymore. Good. The next point is, we already scratched it, discontinuities, because we already talked about impedance mismatch, and this is of course a big topic. If we have changes in the geometry of our transmission line from a narrow transmission line to a wide one, or from a wide from a big volume of dielectric material to a small volume of dielectric material, we have changes in the impedance of the transmission line, and these changes cause reflections, they cause field conversions, and so they create losses for us. How could we analyze how much we lose and where we have the problems? This could be done with TDR measurements, so with time domain reflectometry, and with that we inject a defined pulse into our device under test, and due to the reflections, the amplitude and the time when the reflections arrive, we can recalculate or we can transform it to a curve from impedance over time, where we can see at which point of time we have bigger problems with discontinuities, so with areas where we have bigger jumps or mismatches in impedance, and we can locate that. And the good thing is, and normally the scopes can also do that directly, we can also recalculate from time to length to know about where we have the big problems in our design. This is very helpful, and of course these charts from the time domain reflectometry will be also one of the bases what we have a look on later on in the simulations. So let's summarize the basic RF engineering. The wave impedance depends only on the electric and magnetic field with the parameters epsilon, r, and mu r. Typically it's 50 ohm. With the S parameters, we can measure the reflection and the throughput of the transmission line, and we can detect discontinuities with the TDR measurement, and that way we can identify points where we have problems with reflection. Then the second step we need is PCB structures, because that's of course what we need to know or take care on when we want to match the connector with the PCB. There is some typical layer setups in use. we want to look at. There is some typical transmission line designs we want to look at, and then we will have some tips and tricks what you could take care on to make life easier, let's say like this. Layer setups. So typical uses are 2-layer or 4-layer systems. Of course, there's also higher layer numbers available on the market and used, but that's, I would say, the ones we are meeting mostly on the market. 2-layer systems, typical height of the PCBs is 1.6 or 1.55, so that's very common. And still the most common material is the FR4. Of course, if you want to really go to high frequency, there's other ceramic materials like Rogers, things like that. But we really keep it for the simulations here in the standard, where we look at because the very special ones are really hard to put into a general presentation, let's say, for more or less general guidelines. So in a 2-layer system, you typically have no separate ground plane. Of course, there is no layers in between where you could separate. Whereas for the 4-layer systems, you typically try to use one RF layer plus separate RF ground, and everything that is not fitting to the RF layer comes to the other side and has a separate ground plane. That's a typical thing, but you have to take care, because if you have a FR4 core, you typically have in this layer stack a pre-preg. So this is more or less a small rim of FR4 material on the rim of the copper layer to protect it also over time from corrosion and so on. So this is directly in the manufacturing, so it's a ready-made plate that is put on each other and pressed, and this of course can cause you some trouble as you do not conduct the housing of the connector direct to the ground plane. We will see that the effect of that later on. So if you want to avoid that, you have to order PCB, for example, with metallized sides. That's a possibility to conduct that in a good way. Another thing is FR4 is made of glass fabric and resin. And this is a little bit of an issue if you quickly want to change your PCB manufacturer, because the relation between the glass and the resin, how this combination is set up from the amount of which part is how much, and also the manufacturing environment have impact on the final value for the epsilon R of the material. And so if the epsilon R changes, you have a different RF characteristic. So you have to make sure that you're in the same range. So it's not so easy to just make your prototype at the one PCB manufacturer and then go for the high volume production to another one and just say, okay, order the same thing. It might be an issue and it really needs to be controlled. Otherwise, you could have some issues and some changes of the behavior over frequency. For the transmission lines, typically used, we have strip lines, microstrip lines, grounded coplanar, waveguides, and slot lines. That's the typical ones to be found for RF transmission. Well, strip line is more or less an embedded transmission line between 2 layers of ground. So it's very close from the idea to the coaxial transmission system. It's basically well shielded, but it's not so nice if you have to add additional parts in your RF transmission path, because if you need to add some parts like capacitors, whatever, you need to go out of your transmission line to the top level, enter your part, go back. So the geometry will change a lot there. That's not so nice. This is why many people, at least if they do full RF design, they prefer to have the RF layer on the outside, because if you have to have additional parts, it's easier to realize and to control, and you have less areas of disturbance in your signal path. Very common is the microstrip line, which is on the top side of the PCB, the transmission line, and on the bottom side you have the ground plane. On the other side, or as a next step, very related, you have the grounded coplanar waveguide. So you still have the transmission line and the ground plane here, but in addition, you have two ground plates guiding the transmission line on the RF layer. And finally, slot line. It's in this case an asymmetrical system where you have a signal line and a ground line, but slot line exists in many different variations, also where you have one line top, one line bottom, shifted just half and half to each other. So there's many options, but we will focus today on the microstrip and the grounded coplanar waveguide, as they are the most common ones. Typically, you have a wider line width when you're using a microstrip. Transmission line, very popular or typical use is as application, is the use as antenna fed line. And of course, you have in this case no ground on the RF layer. You have just the signal on the RF layer, and you have the ground on the opposite side. For the grounded coplanar waveguide, it's a little bit different due to the impact of the guiding ground planes on the RF side. You typically also have a smaller line width, and you have, of course, ground connection directly to components if you need to add components, which makes it easier or gives more possibility to adapt parasitics or to compensate parasitic effects of these components. And so you have more possibilities in variation here. On the variation parameters, we will have a look in a second. What you can see here is a simulation 50 ohm line in a 2-layer system with a microstrip line, so 1.55 millimeter microstrip line, and this is the electric field that you can see pulsing. And on the other side, you have the grounded coplanar waveguide, so in a 4-layer system where it's typically used. So you have ground plane left, right, signal line in the middle, and the according or related ground plane here below. And you see that you have a less field spread and higher concentration on the transmission line with the grounded coplanar waveguide here, whereas the microstrip line, the electric field is pulsing in a much bigger area. And for the application example, on the left side for the microstrip, we have the typical patch antenna. In this case, it's a 2.4 gigahertz patch antenna. And for transmission line with additional components needed, you have here the coplanar waveguide with ground. At the top side of the PCB, where you have signal line, you have the guiding ground planes. And here you see the connection for additional components, where you have also cutouts on the ground planes to compensate the capacitive parasitics that's created by the conduction points of the components. So this is very good to realize with a coplanar waveguide grounded. What parameters do have impedance impact on the impedance of the transmission line when using a microstrip line or a grounded coplanar waveguide. So for the microstrip, we have, of course, the substrate height, so the thickness of the material of, in this case, what we are talking about, FR4, but whatever PCB material you're using. And we have the width of the transmission line. So the only parameter we have left when we once decided for a certain PCB thickness is then the width of the transmission line, where we can optimize or adapt our control of the line impedance. And of course, the epsilon r, what material we choose, for sure, but this is also defined in advance. That's the same for the grounded coplanar waveguide. So the substrate height, the distance between the layers and the material is defined in the beginning. That's the base. If this is once done and defined, we can still have influence on the impedance by, on the one side, the width of the transmission line, but also by the size of the gaps between transmission line and the guiding ground planes on the RF layer. So we have two parameters that we still have left after deciding for a certain PCB where we can control our impedance. And this is why this is very interesting if you want to work accurate here together with other parts. What can we do to make things run as smooth as possible? Well, one thing is you can take care where you put the solder resist. Because if you go to high frequencies, even the solder resist has an impact on signal transmission and on losses. Because on the one side, it's an additional layer that you put on top of the transmission line that also has a certain epsilon r that typically is also different from other materials that are in use. The other thing is that if you put the solder resist on top, this is not a really, let's say, very plain layer. It's like if you put it under the microscope, it's on some places thicker, on some thinner, and so you have also a change in the amount of material. This has also impact. So to optimize your signal line, if you go to high frequency, you can keep away the solder resist from the RF line itself and from the guiding ground planes. So if you keep that free from solder resist, it's easier to, or it causes less reflections. That's just number one. The other thing you can do is, if you're working with a coplanar waveguide grounded, you can use a via fence, which means you're putting vias into the guiding ground planes on the RF layer to connect it with the RF ground below. And with this, you get a very stable ground connection. You reduce coupling by concentrating the field spread really in the area of the transmission line, and you create less losses. So that's also an important point. Here, there is, depending on who you ask, there is always a little bit of a difference for the rules how to set up the via fence. In theory, you should have a distance from about 1/10 to 1/20 of the wavelengths to connect the ground planes to the coplanar wave ground. But the thumb rule is to say the distance between the vias is 4 times the gap between the signal line and the ground line. So that's always the question: do you calculate it? Do you follow the sum rule? How accurate you want to be? So next tip, of course, is then to use really to go into a layer system that allows you to have a separate RF ground to your RF layer, so you don't have to share the ground layer with something else, but really have it separated. You have reduced loss, you have no vias, no problems with setting vias inside of your transmission trace. So this makes things easier. You have a good ground connection and you have less discontinuities. And finally, if everything does not help, you can use taper structures. So if you add a connector, for example, you get additional parasitic, capacitive parasitics in the connection area when you put the pins, for example, the connector pin on your defined transmission line, and you have to compensate this additional volume that you put on top of the trace by changing the geometry, by putting away some material, and to set up taper structures to have a smooth transition between the reduced transmission line area and the full width for 50 ohm of the transmission line. So you make these kind of smooth taper structures. You can have them as well on the line, on the transmission line, then it's called line taper, but you can have them also on the ground side if you have a coplanar waveguide. So it's a ground taper. And sometimes if you have too much capacitive parasitics and you cannot compensate it on the top layer with ground tapers, for example, you can also go into the RF ground plane below and create defective ground structures, DGS structures, where you take away some area of the ground plane to compensate the rest of the parasitics. So this is also something that helps, but it's of course more complicated than just be able to work on the top RF layer. Okay, let's summarize the PCB structures. We have talked about the line impedance for the microstrip. We have the impact from the substrate height, the material parameter epsilon r that we have to define before. And when this is done, we only have the width of the line as parameter to have influence on the impedance. For the coplanar waveguide, it's basically the same, but at the end we have two parameters to control the impedance, the width of the transmission line and the gap width between transmission line and guiding ground lines on the RF layer. We can keep the RF transmission lines free from solder resist. We can use separate RF ground, and we can use taper and defective ground structures to optimize our design and to compensate capacitive parasitics. Now I think we covered most of the basics. Let's combine the PCB and the connector. So typical connector PCB combinations are the blunt post for the, let's say, lower frequency in the high frequency area. So for the SMA, I would say let's go to 6-8 gigahertz, but not to the 18. The flat tap for the higher frequency. Typically, we use the blunt post in a two-layer system where we typically have wider tracks, because then we have less bad input from the big pin, and typically it's used then for microstrip lines. The flat tap, in opposite, is mainly used for smaller PCB tracks, where we have then the benefit not to have too much input from the impact from the pin. So typically 4-layer system with coplanar waveguide grounded. And that's the thing, of course, we want to see also in our simulation. What do we have to expect if we combine the connector with the PCB? We have to expect that we will have discontinuity at the connection point, because we will have a big change in the line impedance, and we will have a lot of field conversion, because we have as well changes in the material and the dielectric material from the connector to the PCB. But we also have a change in the geometry from the circular geometry from the connector to the more rectangle geometry of the PCB. This will create a huge mismatch at the first stage. So we need to have a planar matching circuit that takes care that we have a transmission from connector to PCB as smooth as possible. If we look at exactly this connection point between PCB and connector, of course, we have the circular field spread in the connector, and we have, well, the more rectangular geometry here on the PCB side. And what happens exactly in the point where the connector hits the PCB, so exactly the edge of the PCB, so the nowhere between, we have a quite high field spread, because this is the area where we have really this huge change in the geometry and in the materials. What can we do now to optimize this, and how much can you count on a datasheet layout? This is what we will see now in our examples. We do the simulations up to 18 gigahertz for the SMA connectors. And in the first example, we will take the flat tab connector with the hooks in the 2-layer system and microstrip line, and try to optimize it as good as possible. In the following steps, we will take the end loss connector with flat tab and blunt post and compare the effort we have to take in the layouts to make it as good as possible. And we will also see how to manage to optimize the connection with this vertical type that has an SMT signal pin, but THR ground pins to give it more stability in the PCB, because a full SMT vertical version is mechanically not the most stable version. So that's the benefit of that one. And those connectors we will put on a 4-layer system with coplanar waveguide, also here, like we saw before, the 1.55 millimeter PCB. What do we define as borders to say it's good or not good? For the reflection and mismatch, we will allow plus, that's the one thing we will have a look at for the impedance behavior, so from the TDR measurement, and we will allow plus minus 4 dB as this is okay. For the S parameter measurement, for the matching, we will have from 0 to 6 gigahertz minus 20 dB, and from 8 to 18 gigahertz minus 15 dB. So we are in the range that we also saw before in the table, where we had a look at the S parameter values for the matching. That's what we took as base, but of course it's easier to make it to do good in the lower frequency area. This is why up to 6 gigahertz we go down to minus 20 dB. First example, flat tab connector with the hooks into a 2.8 millimeter PCB with 2 layers, FR4 core, and a microstrip line. So the application here is patch antenna. We will show you On the first, what happens if you take the pure datasheet design? Just take the information that is on the datasheet, put it on your PCB, done. The second is, if you try to adapt it in the first step, what can you do wrong? The third step is, how can you do it correctly, or what can you optimize? This three-step solution we just do with the first example. For the others, we will of course provide you directly the good information. This is just to understand once why the datasheet design is not always the optimum design. So if you look on the datasheet for that connector, you only have these two vias given to put them on your PCB, and there is no further ground connection defined. And in this case, it's an arbitrary RF line, so the easiest way to do it, because nothing is given on the datasheet. And this is of course in the nature of things that there is not more details on the datasheet, because the datasheet, or it's not known in advance what kind of PCB setup you're using, what layer stack, and so on. So it's just really the base, let's say, to fix it mechanically, what's on the datasheet is, and that's it. And the rest needs to be adapted to your situation, depending on what you are using, what material, what stack, and so on. And this is exactly why the datasheet layout usually is not the ideal solution. And this is what we will see here. We put the data that is in the datasheet and the arbitrary line into a CST simulation tool, RF simulation tool. And what we are seeing here is the electric field that's pulsing over the PCB. And we can already see, okay, we have some red and orange hotspots, seems not to be ideal. But even worse is, on the backside of the PCB, we can see the electric field also pulsing a lot. Where's the problem? Yeah, we have only the ground connection on these two little holes, but we don't have a full ground connection of the housing of the connector. This means we created a slot antenna here on the rim to the PCB, and this is where we lose a lot of energy on the one side. It's radiation, and this can of course cause also EMI problems with the PCB, with the whole PCB, because with this energy radiation, yeah, this will have impacts also on other parts of the PCB, possibly. If we look on the measurement simulation, we can see in the TDR measurement that we have a huge mismatch in the beginning, where we come to the PCB, and still afterwards we have, well, it takes really some time until there is something like stability. And this is also the outcome if we look at the S parameter measurement for the matching. We can see, okay, in the first area, let's say up to 6 gigahertz, it's okay, but then we are really getting out of range. And we can also see here that with the throughput, we really get a lot of loss here. Let's try to do it better. We learned from that example, we do not really have a good ground connection from the connector to the PCB. So this is what we first want to optimize. So we take care that this full panels left and right from the connector, we create pads, we create something like a via fence. You see there's a via below that to really have the perfect ground connection also to the ground layer below. We make a pad on the bottom side to get the front of the housing also connected here by soldering it to the pad, so that we can close this slot antenna. because that's what we always learn. We need to have a very good ground connection. And now we do the simulation again. And we can see, okay, we got less hotspots here. It's not so many, something changed, but still here in the corners and here in the front, there is still some red hotspots that are for sure not where we want to be. But the good thing is, on the bottom side, we can see there is nearly nothing happen. So we managed to close our slot antenna and we managed to get rid of the radiation. Very good. At least we already reached a part of what we wanted to reach. Let's have a look at the TDR scope simulation. Oh, okay, you see, we have in the beginning where we arrive at the PCB one huge mismatch, but then we get quite well stabilized, not on 50 ohm, but still in range. On the frequency side, on the S parameter side for the matching, we can see, oh yeah, something like 1.5 gigahertz, and then we are completely out of range caused by this huge mismatch we already had in the beginning, and we can also see we created a lot of losses. What happened? Yeah, basically what happened is we created here in the interface where the connector comes to the PCB, we have here a ground panel, and a signal line in between. So what we created in the interface part is here a coplanar waveguide. And this means the gap width here also has influence on the impedance. And so with creating that, we can completely change the impedance behavior of the interface part. And this is why it did not run well and what we have to compensate now. And this is what we're going to do. We keep our optimization of the ground because this was good, but we need to make the transmission line in the interface area smaller and the gap wider here to be back with all the influences on our 50 ohm. And then we have to make a taper structure to come back to our original transmission line width for 50 ohm on the open area of the PCB. So that's what we are doing. So in general, it's always good to have these smooth curves when dealing with RF design, because if you make sharp edges here, it's a little bit as if you try to drive on the sidewalk with your car. You know, if you have these borders, these stones on the border, and you bump against it, and a lot of energy goes back to you instead of using a ramp and driving up. So this is working a little bit like a ramp for the electric field. Good, that's number one. Now we have learned why datasheet design needs to be optimized in many cases, or in most cases. It's not the perfect solution, but we also have learned to take care not only to optimize the ground connection, but also to take care on the transmission line side to really have the full picture of the interface and not only look at one part, and then you can really get good results. Because if you look now, we have less problems, a lot less problems here, nearly no hotspots, only very limited. We still have no radiation on the ground, on the bottom side. So that's still fine. And if we look at the measurement, it's much better. It's not perfect yet, but it's much better. We have some mismatch in the beginning, but then we are in the defined area. And also this is mirrored in the S parameter measurement. We have less losses and we come up to about 10 gigahertz as defined, but still with some small deviation, some small loss above it. We can even go up higher, and this is not the final stage of optimizing. So this is really something where you see this has a big impact on what you can do, because typically the measurement you get from a connector when look into the data sheet, it's the pure connector, but it does not say how good the performance will be when you combine connector and PCB. So our next example brings us to the comparison between the flat tap and the blunt post. We put both connectors, otherwise they're identical, on a coplanar waveguide 1.5 millimeter PCB with 4 layers. So it's an application for circuit design. And here we have to take care, because if we use the flat tap, we have the big benefit that we can make an easy design. It's a little bit more difficult to solder, but from the design it's easier, because with 4 layers coplanar waveguide, we typically have very small transmission lines which fits perfectly to the flat tap design that is very tiny. So we can compensate the little amount of volume the flat tap brings on top of the transmission line. So the parasitics that are created by that, we can compensate them by only doing some ground taper structure. Whereas for the blunt post, we need to do a little bit more, because we try to put a huge pin on this tiny transmission line, which means we first have to create a solder pad for it, that we bring with a taper structure to the original transmission line width, and we have to compensate as much capacitive parasitics on the ground side, so with the ground taper as much as possible here. So it's more complicated in the design. For the flat tap, otherwise what we did, besides what I described for the pin and the ground taper structure to compensate, is we made an optimum ground connection like for the last connector. So we took care that we have a perfect ground match here on top and also on the bottom side. That's it. And if this is done nice, we can see that we have, just by compensating with the ground taper structure and of course the wire fence as you typically do, we have no hot spots here, no big issues. It's working really well. And on the TDR scope, we can also see we are really in a nice range where we want to be. Looks good. And for the S parameters, we can also see up to 18 gigahertz. We are fine below the defined limits. So we really can organize this connector in a way it fits perfectly to what we want it to do. On the other side, if we look on the blunt post, like I said, we have to create these solder pad, adapt everything with ground with taper structures from the pad to the transmission line, but also have the ground taper to compensate big volume. We also optimize the ground connection in the same way like for the other one, for the flat tap. And what we needed to do in addition here, because we cannot put away enough material here from the ground plane to compensate all of the parasitics caused here by this big pin, we needed to also make a defective ground structure in the ground plane below the pin to remove enough material to compensate the parasitics. And this, of course, makes things complicated. So if you're not able to simulate, it's really hard to do. And with that, in addition, we could manage to optimize design in a way that even the blunt post is working with the tiny transmission line and gives a good result over the whole frequency range. But it's simply more complicated. So you can see, yeah, okay, it looks quite good. It's not as good as the flat tap, but still it's quite good in the connection area. And if you look on the measurements, the TDR scope is fine. It's not as perfect as with the flat tap, but it's still all in range. And the same for the frequency range. So it's working up to 18 gigahertz, which is really good. But it's not as good as the flat tap. It's close, but it's not as good. And finally, we want to match the SMT vertical SMA connector with the THR pin to the PCB, 1.55 millimeter. We keep it with 4 layers and coplanar waveguide grounded. So also application circuit design. And what we want to see here is also the one thing on the one side, how to match it, of course, but on the other side also, how much impact does the defective ground structure have? Does this bring a lot of benefit, or is this just the last tiny bit that you could need? We will see. So at first, we still have our structure, coplanar waveguide, grounded with wire fence. Of course, in this case, the wire fence goes circular below the connector housing, as we have a vertical way where the signal goes up. So we just try not to break it and to let it continue to guide the whole signal transmission line. And we have the solder pad for the SMT pin of the connector in the middle. What we have to do also is we have to make a ground taper here as big as possible below the housing. Of course, the space is very limited due to the 4 ground feet, the 4 pins. And the problem also here is that this SMT pin in this connector is quite massive. So if I go a step back, you can see it here. This is really a huge pin that brings really a lot of additional volume on this little solder pad here that we also need to compensate a lot of parasitics, and we don't have this. We have the same situation we like with the blunt post, just in a different geometry. So we cannot remove enough here. We don't have enough space below the connector. So also here we need to make a defective ground structure. You can see here, so here really you see the ground plane, and we really removed below that area where we make the ground taper in a circular way. We also made the defective ground structure to have the chance to compensate all of the parasitics caused by this huge pin. What we do now is we compare the measurements between only doing the defective ground structure here and the result with defective ground structure and ground taper, so both, so that we can see the impact of the DGS structure. So you can see here the blue line is just the ground taper without DGS structure, and the red line is ground taper and DGS structure, so the full package. And you can really see a huge impact. With the DGS structure, we are really, for a vertical version, so bringing the signal in a 90-degree angle off the PCB, I would say we are in a really good range for the matching. But without the ground structure, we create a really huge mismatch. And this was also proved by the S parameter measurement, where you can see the same. So with the red line, with the DGS structure, we can go up to 14, 15 gigahertz with a vertical connector, which is quite good for a first attempt with FR4 material, of course. And without the defective ground structure, well, a little bit above 2 gigahertz, we are out of our specification that we defined for ourselves. Yeah, that's the examples. What can we learn from that? Well, we have to take care which connection or which connector pin to choose depending on the application. Of course, it's possible to use the big one for the higher frequencies, but it's just more work and more complicated. So better to go the easy way, causes less problems and less risk of failure. We have to take care on a good ground connection, but if we work on the ground connection of the connector, we have to still keep the overview and see if we change the general behavior of our interface part, and maybe we also need to adapt the transmission line with taper and DGS structures. Otherwise, of course, if you choose an SMA, choose it by mechanical conditions needed, electrical values, and of course, what are you planning to use as PCB structures and layer setups? Does your choice really fit to your need to allow optimum performance? And don't only look on the connector layout itself, like in the datasheet, but optimize it to your layer stack so that the whole connection area is optimized to your singular situation. Do this by using the tools suggested, line and ground tapers, DGS structures, oh, there is a typo, and wire fences to compensate parasitics appearing. Yeah, that's it for the basics of SMA connectors. Of course, all this theory is not only valid for SMA. We choose only the SMA as it has a wide frequency span, and it's the biggest one frequency-wise we have, and with the widest amount of parts. But the theory is also working as well for all the other types of coaxial connectors we are offering. Of course, the theory behind is the same. Just it's not so complicated if you just go up to 6 gigahertz than if you go up to 18. I hope you enjoyed, and I think now it's time for questions, right, Amelia?
Yes, absolutely. That is correct, Thomas. Thank you so much for presenting today. We're going to go ahead and take a look at what questions we do have coming in. As a reminder, if you have any questions, go ahead and ask them in the questions box. Okay, our first question here. What are the main parameters related to the RF cable, and what are the main parameters related to the connectors?
So for the main parameters of the RF cables, of course, it's frequency range, that's one. The other thing is the dielectric material that are used, of course, inside that have direct impact on that. And what is important parameter, because many times you are limited depending on the connector you're using, what diameters you are able to use for the cable side of the connector. So you really have to take care on that, what you're using here. That's the main ones. Temperature range, of course, is an issue. So you have to know where to use it, what is your ambient temperature, and as well bending radius, because if you know you have to have a flexible solution because it's really bent, or you have to go through narrow corners and stuff like that. You have to take care on the bending radius, but majority is, of course, the frequency in this case. For us, the impedance is not so much the issue, because all the cables we are offering are in 50 ohm, as all our connectors are 50 ohm connectors for the coaxial systems. So there is no choice for the moment. This might change later on, then this will be a major value, of course, but for the moment, as everything for us is in 50 ohm, there is no choice anyway. You cannot do something wrong.
Okay, thank you. Our next question here, what do you consider low frequency and high frequency ranges?
So that's a good question. So for our connector series, I would say the lower frequency area is up to 6 gigahertz, and the high frequency ones are 12 and above. That's what I would say for our portfolio, because this is also where we have the jump in the definition, for example, for the matching of the S parameter, where we say, okay, below 6 gigahertz, it's still quite easy to reach the minus 20 dB, but if you go 8 and above, then the minus 15 is the limit defined, because it's really more critical to reach this and more complicated to reach this. So this is the selection we are doing in that way. Of course, I know in many other areas we talk already about high frequency when we are talking about 100 megahertz, something like that. But as we are talking about connectors that are made for gigahertz transmission, so I would separate this in our portfolio at this area of 6 gigahertz.
Excellent. And we do have one final question here. As a reminder to our attendees, if your question did not get answered, or if you have questions at the end, want to order samples, need a quote, simply reply to our follow-up email, where you will also receive the video on demand. Our final question here: does the gold plating thickness of the center pin affect the reliability? And if it does, what is the minimum thickness that they should opt for?
So yes, it does, of course, have impact, as this decides. So the plating, what I'm using on the contact, in this case, not only on the center contact. So our connectors are completely gold plated in this case. Has impact on the connection force, so on the contact force. I can realize if I have a gold plating with a good amount of gold, then I can make less contact force to still reach a very good connection. And in combination with using for the female part of the contact, so the elastic part that is spread, that is moving when you conduct it, when you use a very flexible material like beryllium gold or copper beryllium, you can reach a high stability over many mating cycles and still have good transmission quality. This is exactly the reason why you have these 500 mating cycles for the SMA. For the exact plating thickness of the gold, you got me on my wrong foot. I don't know it by heart, honestly. I can look it up if you're interested.
Absolutely. We can also get back to that person that had the question. And as I mentioned before, if you have questions, don't hesitate to email us at hereforyou@we-online.com. That's the email address that we'll be sending out the follow-up email. All right. Thank you so much, Thomas, for presenting today.
Thank you very much for the invitation.
Thank you. And thank you, ladies, gentlemen, and non-binary, for joining us for today's Worth Electronic webinar. If you want to stay up to date on our webinars, you can always follow us at we-online.com. You can also follow me on LinkedIn, and you can follow our corporate social media accounts. Don't forget to check out our newest podcast. It's the Worth Electronic What's Up radio podcast, available on Google Podcasts, iTunes, Spotify, all over the place. And don't forget to register for our upcoming webinars. Next week, Fabio Costa returns with Jose Guerra. They will be presenting a question Q&A on connectors in both Portuguese and in Spanish on August 11th. And then our friends from IQD are joining us for practice measurement of crystal circuits. And that will be on Wednesday, August 18th. Register online at www.we-online.com/webinars. I'm Amelia Thompson. I will see you next week. Have a great day.